Now in this video we're going to relate some stoichiometry to our ideal gas law. So let's look at the setup for it, then you'll pause and try. This is going to be my balanced chemical reaction for the decomposition of sodium azide, NaN3. We start out with 2 moles of the solid, which is going to give us 2 moles of the metal and 3 moles of the nitrogen gas. If an airbag has a volume of 36 liters and is to be filled with nitrogen gas at a pressure of 1.15 atmospheres and a temperature of 26.0 degrees Celsius, how many grams of sodium azide must be decomposed? Go ahead and pause the video and give it a try. Okay, let's take a look. Now, first thing I like to do, set up my PV, N, R, and T over here on the side, because I can just lay out everything that I know for the 5 pieces of my ideal gas law. Now, my goal here is to determine grams of sodium azide, and of course to get to grams I always have to go through moles, right? So I know that this is going to be the part that I'm solving for in my ideal gas law portion of the problem. I also will always know that R is going to be 0.0821 liters atmospheres over moles Kelvin. Okay, and this will remind me what I need each of these units to be. So for pressure, I was given pressure to be 1.15 atmosphere, 1.15 atm. That's going to match up with the unit that I need, so I'm set to go for that portion. For volume, I need to get to 36 liters. 36 liters, and that matches up with my ideal gas constants units as well. For temperature, I am at 26.0 degrees Celsius. 26.0 degrees Celsius. I need to be in Kelvin. Remember that to convert between Celsius and Kelvin, we'll add 273 to go from Celsius into Kelvin. So we'll have 26.0 degrees Celsius. We're going to add 273.15. Now remember that this is our addition-subtraction rule for Sig Figs, which means we're going to lay it out. We're going to chop it off at the shortest spot. We'll have a 5 hanging off in the insignificant portion. We'll still have the 1 there. We'll have a 9. We'll have 9 and 2. So 299.15. Now, when we're looking at this, we can remember it either as being 299.1 and show the 5 as being insignificant by doing a drop case on this. And that will help me prevent from round-off error early in the problem. The other way we could think about that is to go ahead and do the rounding now. This is the better way, but I'll show it just to keep us in practice for our round-off rules. Keep in mind that we have 299.15, nothing. Nothing is given after the 5. We have no information about whether this 5 should round up or down. It's right on the dividing line. As a result, we always round to be the even number to take the choice out of our hands. So this would actually round to be 299.2. Oops, that's a 2 right there. Here we are. There, that's better. This would be the shorter way to write it. I'm going to use the slightly more expanded way during the problem. Again, that helps me prevent any round-off errors as I go. Now I'm set to set up my PV equals nRT. So PV equals nRT. We'll set up my pressure to be 1.15 atmospheres. We'll have our volume, I'll go ahead and put it over here, 36 liters. Those are being multiplied. That's going to equal my number of moles, which is a question mark at the moment. My R, which will be 0.0, there we are, 821 liters atmospheres over moles Kelvin. Now, on this side, I can already see that I'm going to be able to cross-cancel my liters in just a moment. And I'm going to be able to cross-cancel my atmosphere as well. So that leaves me with moles and 1 over Kelvin. I still have to put in my temperature. My temperature is 299.15 Kelvin. That's going to cross-cancel. And remember, the reason I was able to cross-cancel these and these despite them being at the same level, if I divided the liter back over here, now it would be liter divided by liters. So if it's at the same level on the fraction on opposite sides, we can cross-cancel them immediately. We haven't done that a lot in our fence post approach for other problems, but we get to do it in this sort of a problem here. Now, I'm ready to go. The only thing I have left is number of moles. I'm ready to grab my calculator. Okay, so let's go ahead and do it. On the left side, I'll have 36 times 1.15. That's going to give me 41.4. So I'll go ahead and I'll write it in. 41.4. No units because I've already cross-canceled them. Now I'll have my 0.0821 times 299.15. That gives me 24.56. Okay, so I'm going to be down to 3 sig figs. I have 5 here, but 3 there. So I'm not going to worry too much about any trailing values anymore. So I've got that. I know that my n is going to end up being in moles. So I'll just be super rigorous by writing 1 over moles, since it's the only thing I have left in my units. Most of the time people don't do this, but I think it's good practice to do it anyway. So we're going to have that value times n. Now all we have to do is divide this over to the other side. Notice that when we divide, this is going to flip back upright, and we're going to have number of moles in moles. So we'll grab our calculator, and we'll have our 41.4 divided by the 24.56, and that gives us 1.67, and equals 1.67 moles. So we're in good shape so far, but let's revisit what we've just calculated. We've determined how many moles of gas we have. Right here's the gas in that equation. However, I was asked for grams of sodium azide. So now what I need to do is go through my conversion factor, get into moles of sodium azide, then use the molar mass of sodium azide to finish the problem. So I have 1.67 moles of N2. Let's set that up. I'm going to have 3 moles of N2, giving me 2 moles of sodium azide. There we are, sodium azide right there. My moles of nitrogen have cross-canceled. I'm in moles sodium azide. I'm ready to go from sodium azide moles. Oops, I didn't write moles right there. There we are. 2 moles of sodium azide is on top. Now I'll have moles NaN3, and I want to get into grams of NaN3. There we are. And for that, I'm going to need a molar mass. So I need to come up and calculate my molar mass for sodium azide. I'll have a sodium. I'll have a nitrogen. I've got 1 sodium, 3 nitrogens. Let's see, sodium has a mass of 22.99. Nitrogen has a mass of 14.01. We'll multiply across for that. That'll still be 22.99. And this one's easy enough to do in my head. 3, 0, 0, 2. 3 plus 1 is 4, 4203. We'll add down, and I'll end up having, let's see, 2, 0, 5, and 6. 65.02 grams per mole. So I'll have 65.02 grams per mole. Ready for the calculator again. Okay, and you can see I still have my trailing insignificant figures there, and that's fine. So I have that. Said times 2. Then divided by 3 times 65.02. It gives me 72.53 or 54. 72.54, 2.54. I have 3 sig figs, exact 4 sig figs. I'll be chopping that to 3 sig figs. Final answer for this should be 72.5. There we are. grams of sodium azide. That's how we'd finish solving that problem. Let's see, and actually, if I look carefully back into my sig figs, it looks like I've made a Sig Fig error. Notice that I had 2 sig figs for my volume. That means that when I plugged all these in, I should have only had 2 sig figs in this piece, 2 significant figures here. That means I'm actually down to 2 significant figures, so when I carried it all the way through, I should end up being at 73 grams of sodium azide. There we are, because I should have been chopping off right here. This is higher than the 5, which means it rounds upward. That's how we'd solve the problem for how much sodium azide should be charged inside of our airbags in our cars.